Great, welcome back. In this last lecture, I want to talk a bit about weak lensing, and as has been the theme of my lectures in general, again focus on the systematic uncertainties and analysis aspects, rather than going into detailed calculation and theory calculations, even though those can be a lot of fun. So let's just briefly agree on the basic geometry and how lensing works. We start out with some source. In our case, later that will be background galaxy. Light, of course, propagates in a straight line, passes by some overdensity and gets deflected, so that the source that we would not see otherwise goes into the telescope. And then we know that this deflection angle here, alpha hat, is 4gm over impact parameter. And then for the observational aspects, if we now then just continue this, we know that we will actually observe the image being located over here. Now, what matters at the end for the observations are the angular coordinates. And let's just call this angle leading to the image here theta, while the undeflected path to the source, here let's call that beta. So then this difference here, that's of course our proper deflection angle, or the observed deflection angle, which will be some scaled version of alpha hat over here. And we can calculate that with basic geometry. First, just looking at the distances here in the background. So we can directly see that the distance to the source. So basically, we will use this distance here at the source times theta. All right, so that is just basic geometry, but we can then, of course, realize that our observed deflection angle then simply becomes the lens source over the source times the times alpha hat. And I'm doing some coordinate transformations into co-moving coordinates, making sure that we then, when we talk about distributed masses or deflectors, that we take care of proper versus co-moving densities. In the end, this will become something like chi source minus chi lens over chi source times the differential deflection at a given location. So that from that comes this factor in the lens equations often. So often you will see something like 1 minus chi over chi source or something when we then later do this in a cosmological context. But that comes just from the very basic geometry of the lensing. That's our setup. And in particular here, we will now really consider weak lensing of galaxies. So let's, for now, imagine that our background galaxies are all perfectly circular. And then the light gets deflected on the way to the telescope. And we end up with distorted images. So our galaxies appear elliptical. And in particular, these ellipticities will align tangentially around overdensities. So at that point, I will just say that the observed ellipticity at the end is our intrinsic ellipticity plus gamma, a gravitational shear. And the statistical properties of this shear then reflect the statistical properties of the density field. Is there a question? Good. And in particular, we can write our deflection angle, alpha, now as a line of sight integral over the derivative of the metric potential. where again here we have our geometry factor telling us how efficient lensing is at different combinations of lens and source redshifts. Throughout this, we'll use the Born approximation, which means that we integrate along the unperturbed path, which turns out to be an absolutely excellent approximation. That was one of my first practice projects at the beginning of grad school, doing this to fourth order, and I can tell you, yes, even Euclid and future surveys will not have to worry about it. Definitely safe. But so with that, we now know that all this lensing can be basically captured in lensing potential and its derivatives, like the deflection angle. And of course, there's then a bunch of relations that we could derive of these various quantities that govern weak lensing, but that will not be my focus today. I'll focus again on the observational aspects. But there are some excellent lectures by Bartelmann and Schneider from the late 90s, early 2000s that go through this in great detail. One thing that is useful to really see about weak lensing, though, is this distortion tensor, Aij. And for that, we're just considering basically the transformation from source to image plane. So we're looking at how basically just checking how alpha changes here as we move through the image plane. And after some algebra, we can then write this distortion tensor in terms of basically two P quantities, kappa, a scalar, and our gravitational shear, which has two components. To figure out the basic effects of weak lensing on a galaxy, we can then just start using this distortion tensor to figure out what happens to a small galaxy. And of course, the important thing here is that weak lensing only deflects the photons. It does not destroy or create photons and does not change wavelengths. So that means that specific intensity is conserved. And we can simply do a remapping between the source and image plane. So that means for a small source, we can then do a Taylor expansion, doing this remapping in terms of the image coordinates and our distortion tensor. After that, it's a few lines of algebra to check what happens to a small circular source. And in particular, that will turn into an ellipse with the semi-axis related to the eigenvalues of A. That's where the shear comes in, and the orientation is also determined by the shear components gamma 1, 2 directly. And similarly, if we now just think about the one of these axes, A of the source and image. Oh no, sorry, if we think about the area here, that gets, of course, also distorted or rather magnified in this case. In particular, there the determinant of our distortion tensor comes in, and we realize that the area of the image is a factor mu times the area of the source. So that is, besides shear, the other main effect. And in particular, we then can say that lensing shears the image, meaning that one axis contracts and the other expands. It magnifies the image, making it appear larger and brighter. Oh, and I didn't finish that sentence. And it changes the density of sources simply due to the geometric refocusing. In one picture, let's start out with a uniform grid of circular background sources and put in a massive deflector. They all then all these sources appear pushed outward away from the lens. Close to it, you can clearly see how they get larger and brighter. That's magnification. You can weakly see maybe that they also are aligned tangentially. And obviously, the apparent density of sources changes. And in principle, one could use all these different effects to measure weak lensing. But let's just say we have a galaxy field without lensing and a galaxy field with a lensing strongly exaggerated. Now, to actually do precision cosmology with this, of course, we need to have some basic understanding of the unlensed galaxy properties. And while we could try to measure lensing using any of the observational signatures, shear is the most prominent one because we know a priori that the intrinsic shape of a galaxy, if we write it as a spin 2 field, is averages out to 0. If galaxies are randomly oriented, then averaging over a bunch of intrinsic ellipticities gives 0. And any non-zero average over the apparent shapes of galaxies in a small patch of sky then should be our gravitational shear. Or we don't have such a priori assumption about the density of sources or the size and brightness distribution. And that's why most of weak lensing so far has been done using shear. There is a small body of literature measuring magnification, and that relies on scaling relations for galaxies, say using the fundamental plane, but that is something that is not done at scale because it would require much better observations than basic imaging to get the shapes of galaxies. Often then it's when we continue with shear, which is directly related to convergence. Let's just get clear about a bit of the math. This convergence field is at that point a simple line of sight projection of the meta density, again with our lensing geometry kernel. And let's just write all these prefactors here as a radial kernel W. Then we can go on and average this lens efficiency W over a broad redshift bin, which is just a simple integral averaging over this distribution n of z. And with that, we can then, in a compact way, write the angular power spectra of the convergence in terms of these tomography bin averaged lens efficiencies, Wi and J for the two different bins, and the meta power spectrum. That looks like a pretty neat probe of cosmology. Basically measure kappa, and with that we have a measure of the meta power spectrum without assumptions about galaxy bias. Problem though is typically, at least in the current generation, these redshift distributions are pretty broad. Shown here is an example from the DS analysis, which means that this lens efficiency W is a very wide filter. So even for our smallest, lowest redshift bin, shown in blue here, that means that it really will average over contributions between a redshift of order 0.1 to 0.3 or 0.4, and mix a bunch of modes. And that gets even blurrier as we go to higher redshift, which means that in the end, our angular power spectra are rather featureless. So clearly, that limits the amount of information that we can directly extract about P delta from these kind of curves. But nevertheless, I'll take you through what we can learn from it and what the other ingredients are next. Since I'm tasked with data analysis, let's briefly also talk about how we measure shear two-point statistics in practice. So far, weak lensing has mostly been measured in configuration space for very practical reasons. And that is that a lot of the systematic effects are things that really happen on characteristic scales in the telescope. So isolating them in configuration space often is easier for observation diagnostics than first transforming the shear field to Fourier space, where you also have to be very careful about E and B mode mixing. So that means we really want to measure 2-point functions. We start out with a pair of galaxies, and we want to correlate their shears. At that point, our one preferred coordinate system is the line connecting these two galaxies. So with respect to that coordinate, we then define our two shear components. That is, basically we will define one shear component to be along this connecting line, and the other component to be at 45 degrees. Where, of course, perpendicular here is for a spin 2 field, so that's at 45 degrees. And at that point, then, we know how to combine the two shears into a 2-point function. That is, we combine the two tangential shears, the two cross shears, and then we can put them together with either a plus or a minus. And those are our two shear correlation functions that are parity invariant. On the other hand, gamma t, gamma cross vanishes due to parity. That's the idea. In practice, that means, again, that we just sum over the ellipticities of a catalog, again, with some weight assigned to each galaxy, similar to what we discussed for the imaging systematics in galaxy clustering. Here, again, it is also related to survey completeness and depth and such. And with that, we have a simple estimator for our shear correlation function. On the theoretical side, then, psi plus and minus are related to our shear or convergence angular power spectrum with a simple Hankel transform. And the psi plus and psi minus then just have J0 or J4 as the radial kernels, because those are different derivatives. Importantly, psi plus, which transforms as J0, is then sensitive to lower K modes at the same angular scale than psi minus that transforms with J4. So at the same angular scale, these two probe somewhat different scales in Fourier space. But still, of course, if you start out with a rather featureless angular power spectrum, you also end up with a rather featureless angular correlation function. So this doesn't magically create clear signatures for different cosmology parameters. If you were to use all scales, of course, the information content would still be the same in Fourier and configuration space. So if we now want to do cosmology, that means that cosmic shear by itself primarily really constrains an amplitude rather than shape parameters. And that is why weak lensing results primarily report a parameter S8, which is a combination of sigma 8 and omega m, which makes a lot of sense because, of course, we have a projection of the matter power spectrum. And then because lensing is by overdensities, we get a prefactor of omega m rather than just a dimensional density contrast. So that's the combination that we really probe. And I will then take you through the process of how these contours actually happen. As an aside, constraints on parameters like NS or omega b or h from cosmic shear are pretty abysmal. So that's the case coming back to yesterday's lecture, where informative priors really are your friend. And most of you have probably heard that, or can also see in this plot here, that there has been discussion whether there's an S8 anomaly or not, in the sense that different weak lensing measurements from 3 different galaxy surveys tend to be at lower S8 values than the Planck CMB results. And that has gotten even more intriguing because this appears to be only the case with galaxy lensing, not with CMB lensing, shown over here. So we can't fundamentally say that this has to be a effect associated with weak lensing, but to understand whether this is new physics or new systematics, we also have to understand what's the difference between CMB lensing and galaxy lensing here. Because in principle, they should just both probe the background evolution and the metric potential. So let's talk about how the sausage is made, what really goes into cosmic shear analysis. So that you get some more tools to judge those papers for yourself. Of course, the question is, how do we measure an ellipticity of or how do we measure shear? And that translates to measuring the ellipticity of a galaxy. The first step is to measure the centroid. So that means we will just take some integral or sum over the pixels that have been associated to a galaxy and just find out the centroid position. And the next step, then we can measure the second order brightness moments. That's again just a sum over pixel values. Problem, of course, is what I'm hiding here is that first of all, you need to detect your galaxies and decide which pixels really belong to the galaxy. And that is quite a tricky problem that could be easily 2 or 3 lectures by experts who really work at this pixel level. But let's just assume for now that we've somehow decided which of these pixels belong to a galaxy. And I should say that in order to include as many galaxies as possible, of course, you want to go as faint as possible. So we're not talking about nice, beautiful spiral galaxies here, but about fuzzy blobs with signal to noise of maybe 15. So that might be just of order 6 or 7 pixels. And then once we've constructed our second order brightness moments, we can define an ellipticity measure. And that's really a choice of definition. A few different conventions exist in the literature, and that's fine. Now that we've defined an ellipticity in some way, we can think about how the observed and intrinsic ellipticities are related under lensing in these different definitions. So we, of course, know how our second order brightness moments transform. That is just this quadratic transformation here with our distortion tensor. And then we can go through a few lines of algebra to understand how our source ellipticity in the 2 different definitions relates to the observed ellipticity and the shear. Then the next important ingredient that we still need is that the universe is isotropic and galaxies are randomly oriented, so that the intrinsic ellipticity on average is 0. With that, we can then say that the gravitational shear is simply related to the ensemble average over our ellipticities. Beautiful. And let's get to reality. So we start out here with a galaxy. In this case, of course, that's a big beautiful galaxy, not just a signal to noise of 15. And we also highly exaggerated the weak lensing effect. In reality, that's about a factor 50 smaller. But you can see by eye now how the electricity changes. Then it goes through the atmosphere and into the telescope. So it gets blurred. And then it gets pixelated in the detector. And there's also noise on top. So you can see how even this quite beautiful galaxy with high signal to noise is extended, ends up being of order, I would say, 25, 30 pixel here. And our task now is to do this inverse problem, figure out from those pixels there what the shear in this step was. The key tool that we use for this are stars, because that allows us to really measure this important PSF convolution and understand what the atmosphere and telescope are doing to distort shapes of galaxies. So basically, at least from stars, we can then reconstruct this step and also get a better understanding of the CCD pixelizations. Unfortunately, of course, this process will always be imperfect. So in the end, the common parameterization is just saying, well, our inferred shear may differ from the true shear by some multiplicative bias and an additive term. And our task then will be to figure out as closely as possible what these biases in a given shape measurement algorithm are. Let's look at a little bit of data here, just to get some sense of what we're talking about. In HST imaging, which of course is limited to small footprints, a typical star might look like this. In a typical galaxy used in cosmic shear analysis, like this fuzzy blob over here. I see some raised eyebrows, but it gets better. At the moment, when we do this at scale, we use ground-based data. And that is still quite a step down compared to HSD quality. So here is a typical image from the dark energy survey, covering of our order 2.2 square degrees. And that's the type of data that we're currently doing weak lensing measurements with. When I first went DES observing, after having done a paper and pencil PhD, and looked at stuff like this, I realized, okay, in weak lensing, it's probably not time for fourth order corrections yet. There's more relevant things to deal with first. So does someone want to guess how many galaxies should be in this field of view here? Above or below 10,000? Raise your hand if below. 100,000? 200,000? 500,000? Yep. You can, of course, calculate this because I gave you the field of view. And the typical source galaxy density is about 10 per square arc minute. So it's a few 100,000. But that still, of course, is a lot given what this data looks like. So now to actually do weak lensing cosmology, we need to put in all the astrophysics and systematics that are not directly apparent from this simple equation. We will, of course, we have these redshift kernels there, which depend on the redshifts of our source galaxy distribution. And these redshifts will always be approximate, coming back to what we discussed in lecture 1 already. Additionally, the source galaxies may not be randomly oriented because, of course, they form in cosmological environments, and that means also in large-scale tidal fields. And P delta here is the total matter power spectrum. That includes all of nonlinear evolution and baryonic effects. So going from even from what we would measure as P delta here to cosmological parameters is also not as straightforward. Repeating basically a slightly different version of a plot from lecture 1. When we think about how to back out cosmology parameters from the matter power spectrum in the highly nonlinear regime, then we really have to worry about baryonic feedback processes. Showing here now an even extended compilation of different hydra simulations and how they modulate the matter power spectrum. So at K of 10, that's of order 20 to 30% differences in the matter power spectrum. Two ways to deal with this. We could include them in a model or throw out all the small scale data. And I'll talk about those two options later. Of course, then additionally, there's uncertainty in the gravity-only nonlinear matter power spectrum that we somehow need to grapple with. Next up, intrinsic alignments, which Misha already mentioned in the previous lecture briefly at the end. Let's first look at the easy case here. That is an elliptical galaxy. And for elliptical galaxies, we know that the galaxy shape approximately follows the halo shape. So if we consider a halo forming in a tidal field, it is easy to imagine that that halo will get stretched and not be spherical. So that means that the intrinsic shapes of our elliptical galaxies align with the tidal field. And for two sources at the same redshift, that would mean that they would boost the shape correlation. If we only had sources at the same redshift, that would mean that we inferred it as as too high. But there's also a more subtle correlation across redshift bins. For spiral galaxies, this process is a bit more difficult because the direction of spiral galaxies is determined by their spin. So to calculate how the spins of two different galaxies align or may align with the tidal field, we'd have to do tidal torquing. And that's a second order calculation that doesn't neatly fit into a lecture. But there are channels through which these galaxies could align as well. So in addition now to two galaxies at the same redshift being positively aligned, there could be another effect. And that is we could also have a correlation between galaxy shapes and foreground shear. So let's start out with some galaxy in the background, which then on the way to us gets lensed by some foreground structure. And we have another galaxy at the redshift of our lens that's forming in that tidal field of this overdensity. So that means that this galaxy here, if it's an elliptical, would align radially with the overdensity, while the background galaxy gets lensed and aligns tangentially. So at that point, we get an anti-correlation between background shear and foreground intrinsic ellipticity. So, sorry. Yeah. Now, if we add this into our weak lensing power spectra, we get some modification. And in particular, it actually tends to lower the shear power spectra because this background-foreground correlation is more significant than the shape correlation at the same redshift. But unfortunately, the resulting power spectra are still pretty featureless. So that probably still limits us to mostly getting an amplitude out of it. But one thing that's really useful to keep in mind is that intrinsic alignment is most relevant at low redshifts. This weak lensing kernel here, that gets more efficient at high redshift, while intrinsic alignment is a purely density effect. So that means that it is most efficient, compared to this kernel, it is most efficient at low redshifts. If we were, for example, to do cosmic shear only with galaxies above redshift 1, then we basically wouldn't have to worry about intrinsic alignments. But with the current generation of surveys, of course, that's not an option yet. So since weak lensing would probably mostly tell us about one amplitude, current generation of surveys supplemented by other correlation function measurements that we can get from the same photometric data. In addition to this shape-shape correlation, we also consider the position of galaxies on the sky. That is, we consider both galaxy clustering and a cross-correlation between our foreground galaxies and background sources. That's galaxy-galaxy lensing, which basically allows us to measure halo masses for the foreground galaxies. So top one just measures matter power spectrum. Second one, as leading order, is B squared matter power spectrum. And this one is just B times matter power spectrum. So that means that by combining them, we can separate power spectrum amplitude from galaxy bias, which allows us to break a lot of degeneracies. This black contour here is an example forecast for how well we would do in sigma 8 or S8 and omega m with cosmic shear only. This blue contour is combining the latter two, galaxy clustering and galaxy-galaxy lensing. And then red, what we get when we combine them all. So there you see how combining the different measurements really helps improve cosmology constraints. primarily by breaking the sigma 8 galaxy bias degeneracy. All right. Of course, this is quite a bit of work. And in our most recent DES analysis, we needed 30 papers to describe the various steps of the image reduction, shear measurements, photometric redshift estimation, modeling, cosmology inference, and so on. We started out with a Gantt chart that was a vast underestimate, so this got much more complicated in between. But at the end, we end up with this beautiful pipeline. Of course, all starts with photons coming into the telescope. Then we turn them into images. The next step, we separate galaxies from stars, throw the stars away, write papers about the galaxy catalog, and then we weigh those galaxies, which means we measure their shapes. We also measure the estimate of photometric redshifts. And then we combine them with theoretical models and simulations and a few covariances, and out come cosmology parameters. I will share my slides, so if you want to at least read the titles afterwards of all the papers that correspond to this nice flowchart, you can. I will just take you through some of the high-level aspects here. But since I led the DES collaboration at that time, one of my tasks was to make sure that all these 30 papers were consistent in notation, how they talked about results in many subtle ways. For example, when the two cosmic shear papers came onto my desk, one of them was still writing about S8 tension between weak lensing and Planck, and the other talked about agreement between weak lensing and Planck, which probably tells you that it's nothing to write home about yet, but those are the kinds of tasks that one ends up with at the end. So let's start with the source galaxies and the related image process or data processing steps and systematics. Often when you ask people what's the biggest worry in weak lensing, they will answer photoses. I tend to agree. So I'm very happy that DES really did a very extensive work characterizing the redshifts of our source sample in year 3. And for that, we relied on complementary parts of information. We used photometry in the form of galaxy colors of different types. We used the spatial distribution of these galaxies. That is, we use cross correlations with a known sample, or with a sample with known redshifts, knowing that the cross correlation will peak when they are at the same redshift. And we also use some version of lensing that is relatively insensitive to cosmology, but really sensitive to the redshift distribution by taking the ratios of the lensing effect at different redshifts. Now to get photoses, we basically do a multi-step calibration process. There are some small patches of sky shown here in red, for which we actually have spectroscopic redshifts. Around those, we then have very deep imaging in also additional bands compared to the main DES imaging. So these are our deep fields, which means that we have more filters and less photometric noise, which otherwise is a leading uncertainty in redshifts from shallow data. And then we do image injections. That is based on information from these deep fields. We generate images in the shallow imaging to really understand the transfer function and what basically the role of photon noise. So at that point, of course, we have redshift estimates from the deep data. And then we use this injection from the deep data, so basically the accurate colors to the approximate colors, C hat, to characterize this transfer function so that we can interpret our distribution of observed noisy colors C hat. And from that, in the end, we then get an estimate for the redshift distribution in our assigned bins. As a result of that, we then get an estimate of the redshift distributions for these tomographic bins, where these violin plots show the uncertainty at different parts of the distribution. Of course, there's still a lot of uncertainties in this process. So also as a guide, as information for future surveys, we really drilled down what's important or what's the limiting systematic. And in particular, we looked at the sample variance, that is the limited number of redshift samples, shot noise, photometric calibrations, this transfer function or image injection process, and general assumptions in the method. So it turns out that currently these constraints are primarily dominated by sample variance. And then one of the next leading factors is photometric calibration. So that's clearly something useful to know for people working on future surveys, what I guess is in the top wish list based on the DSC3 perspective for what to improve. In the next step, we combine this purely photometric information with cross-clustering. So we have our wide tomographic bins of the source sample, and then we do angular cross-correlations with galaxy samples with much better known redshifts. And we check where that cross-correlation peaks. From that, we can then further shrink the uncertainties in these redshift distributions. Of course, we also have to measure shapes, and we have to measure shears in a way that goes beyond just defining simple second-order brightness moments. And in particular here, we measure the response on elasticity of our elasticity estimator to artificially applied shear. So we start out with with basically our actual galaxy, then we deconvolve the PSF, apply an artificial shear, reconvolve, and measure the electricity again. And that's an unbiased estimator in the limit of weak shear, isolated galaxy images, and perfect knowledge of the point spread function. Of course, most of these assumptions don't really hold. So then we have to use a large set of simulations of galaxy images, in part some that are overlapping, to calibrate biases in our shear estimation. With that, then we end up with 100 million galaxies for which we measure shapes. This image shows you here how our data set increased from science verification to year 1 to year 3. Importantly, here we have more accurate point spread function modeling, improved astrometry, a vast suite of null tests, which, for example, involves cross-correlating galaxy shapes and stellar shapes, which would tell us about a spurious signal from the point spread function, because, of course, stars are point sources and definitely uncorrelated with galaxies. And there was massive effort going into calibrating these uncertainties in the shear measurements through image simulation. And the good news is all these observational systematics are so well calibrated that we think they're subdominant. Let's primarily focus on the plot here on the right. Green is our actual constraints. And then we reanalyze the data in a restricted parameter space. If we do not include our modeling of overlapping galaxies, blends, unfortunately that has a limited impact compared to doing the full blending treatment. And by contrast, if we did not account for any shear systematics at all, though, that would lead to maybe 0.3 sigma bias. And we did similar, yes, the multiplicative. We can measure the additive bias more directly, and that is consistent with 0. So including multiplicative bias matters, but the different flavors of how we include overlapping galaxies don't matter. So that that modeling is good enough. If we did not include redshift uncertainties at all, we again would start out as this dashed red line, the dashed yellow line, sorry. So that is a bit of a bias, but not as terrifying as I would have thought initially, actually. And then a somewhat simplified versus full treatment both give quite consistent results. For galaxy clustering, we have two different samples. One is a large red galaxy selection called red magic. That's based on template fitting to the red sequence. That's the magic. And then MACLAM is a bright selection that's basically a redshift-dependent magnitude cut. Those result in, of course, somewhat different redshift distributions. MACLAM extending to higher redshifts. We can't do that for red magic because that 4,000 angstrom break moves out of the DS filters. And for both of these samples, we proceeded measuring galaxy clustering and galaxy-galaxy lensing. Importantly, we found huge contamination from imaging systematics, in particular at high redshifts, where the red crosses here show the signal before imaging systematics correction, and green after. So that clearly is something that we realized early on, oh, there may be quite a bit of contamination in our lens galaxy sample. And then, of course, we do Bayesian inference, as we discussed yesterday. We need our likelihood with a covariance. And there is a beautiful paper that by the covariance subteam checking that the Gaussian data likelihood is sufficient and that the Halo model covariance is also sufficient for our application. Then we need a model and parameters and priors. We need criteria which measurements to combine. And we agreed on a blinding scheme to minimize observer bias. So for these somewhat more theory and reanalysis adjacent parts, I thought I would take you through in some more detail. In particular, because I got so many questions about covariances yesterday, let me briefly highlight what we did. So our baseline is using a Halo model-based covariance shown here for the two shear correlation functions, galaxy-galaxy lensing and angular clustering, compared to a covariance estimated from log normal simulations. You can't really read anything off this plot besides saying there is no obvious bug in the ordering of things in the Halo model covariance. Structure-wise, these will always look quite similar. And that's simply because shape and short noise is so high that really basically dominates the off-diagonal structures. But then the covariance modeling team went through a bunch of different covariance modifications to check both how much do they matter for the goodness of fit, chi-squared, and then in later parts of the paper also how much they may bias parameters. So then they checked a bunch of modeling assumptions on the top first. If we would not properly account for the binning of correlation functions and just say evaluate at the bin center, that would be our most significant mistake and underestimate the chi-squared by 18%. The connected 4-point function, on the other hand, does not matter at all, basically. You see there the comparison between Gaussian versus Halo model and normal versus Halo model, no difference. Doing all these computations on curved sky is currently also not that relevant, given that we stop at about 200 arc minutes, and most of the constraining power comes from smaller scales. Using non-limber and redshift space distortions when calculating angular clustering matters a tiny, tiny bit. The non-Gaussian likelihood is fine for our curve, for our current area. If we had 5 times the current area, that would become important. We also find that it's quite irrelevant at which particular cosmology we evaluate the covariance, so that's good news. Short noise modeling and whether a galaxy short noise is a non-Poisson matters to some extent. And Again, one of those annoying to do, but in some sense straightforward things is masking and survey geometry, which is starting to become relevant. And I must say this paper is one of my favorite ones from the DSU3 batch. So if someone is interested in testing covariances, I think I would highly recommend it. Friedrich et al. Now for the theoretical model, we started out by first writing down the general formalism for computing our angular power spectra and angular correlation functions, and then being very explicit about everything that we had to plug in to evaluate it, and actually do it numerically. So basically for every function that we filled in with cosmological predictions, we ask, would there be a different way to do it? Just so that we are really clear about our choices that we make in, say, choosing a nonlinear meta-power spectrum and choosing a particular astrophysics model. And then for each of these choices, that basically mean here is something where we could have model misspecification, we check how much it matters. And in general here, we consider two types of systematics. One is known but unmodeled or imperfectly modeled systematics. So it could be baryons or imperfectly modeled nonlinear modeling, which we deal with by throwing out data points, that is by scale cuts. And then for others, we have truly imperfect parameterizations. For example, in galaxy clustering, of course, we have to assume not just a scale dependence of bias, which is what Misha discussed, or of galaxy clustering, which you could get through higher order biasing. But just important is that we also, of course, need to assume a redshift dependence. And for that, EFT will not help you. At that point, you really need to understand your galaxies. In our analysis, we assume piecewise constant galaxy bias, linear bias. But of course, we don't claim that's a statement about galaxies in the universe. We need to then check how much this assumption matters. Similarly, we choose imperfect parameterizations for intrinsic alignments and everything else. So just an example on scale cuts. Here you see the cosmic shear angular correlation functions, where the scale cuts are driven by baryon feedback, which in this analysis we don't include at all, and then also by uncertainties in modeling the fully nonlinear meta-power spectrum. So in the end, we throw out about 40% of the signal to noise in cosmic shear. For galaxy clustering, our default analysis uses a linear bias model, so we remove data points where nonlinear biasing becomes significant. Then something we briefly touched on yesterday already. We need a clear plan for quoting consistency or tension. And there we have different strategies for internal consistency. So basically different subsets of our DES data and agreement or disagreement with external data sets. So within DES, both to check the goodness of a particular fit, say in the cosmic shear only analysis, we of course have our data points and can look at the posterior predictive distribution from the fit to shear itself. And we also can use this to assess the consistency of different parts of the DS data. So for example, we could look at cosmic shear compared to the prediction for the shear measurement conditioned on galaxy clustering and galaxy-galaxy lensing. And we agreed to accept the model fit if it corresponds to a p-value of larger than 0.01. That's obviously not a fantastic fit, but the threshold we set for ourselves. And if and then after unblinding, of course, we want to get the best possible cosmology constraints by combining DES with other data sets. But that's, of course, only allowed to combine if the data sets are consistent. Otherwise, the parameter constraints are pretty meaningless, because clearly our model is insufficient. So then we agreed to use a mix of, or a combination of both parameter differences in cosmology and evidence-based methods to do a comparison directly in the full parameter space to quantify consistency with external data. and we will only combine if the p-value is larger than 0.01. And importantly, again, we already made the list of what external combinations we would try beforehand. Because otherwise, if you have a contour, we know Planck is over here, if ds is here after unblinding, and we only then decide what to combine with, we might choose, say, BOSS over here, or another weak lensing experiment over here to maximize or minimize tension. So that plan of what to combine with needs to be clearly spelled out beforehand. And of course, these different combinations should be physically motivated. Of what do I learn from combining with another weak lensing measurement versus what do I learn from combining with BOSS or so. And that's really a part of trying to minimize observer bias. That is, we have a blind analysis protocol. Of course, most of these algorithms go through many iterations. We had many different versions of the initial catalogs and then going to correlation functions and developing our particular parametric model and inference process. And we want to make sure that our tweaks at these stages of the catalogs, of the correlation function measurement, and of the parameter inference or modeling are not driven by what each change does to the final constraints. It is totally fine to say, well, let me revisit, say, this part of our modeling, and someone arguing we really should be using HM code instead of HaloFit, based on some arguments that they've developed that are importantly independent of what it does to the final results of the DS analysis. Because otherwise, this could lead to implicit biases and people tuning the model or an algorithm until they get the result that they want. So that means we put in a bunch of restrictions at the different analysis stages that prevented us to see what algorithm changes do to the final result. And then we only looked at the parameter constraints after the data vectors and modeling were frozen. We'd also finalized a list of model tests and combinations with external data before unblinding. That sounds like simple rules, but it was truly a roller coaster ride. Because at the first unblinding telecon, we had quite a surprise. So the dashed lines here are what we, the first lens sample that we looked at. That's the red sequence sample, red magic, where we have cosmic shear, that is independent of the lens sample, of course, and here the combination of galaxy clustering, galaxy-galaxy lensing. And yeah, we were very surprised to see that the galaxy clustering and galaxy-galaxy lensing combined ended up at an S8 of about 0.65, while somehow the combination between a cosmic shear and this analysis, so the full 3x2 point, these black contours over here, are I guess, fine or match our expectations. And after long investigations, we think we now found some imaging systematics also biasing the redshift estimates of the red sequence galaxies, which we think can in part explain these contours. But at that point, when we just look at these numbers, what do we do now? So to give you some scale of timeline, we unblinded in early November of 2020, and then the results came out late May of the next year. So we took quite some time. But importantly, we had agreed before unblinding that this original result has to be published, and that we clearly have to lay out any steps that we take after unblinding in the paper, so that people can judge for themselves whether they believe our post-unblinding changes. So let me come back here to this PPD diagnostic. And of course, hindsight is 2020. There's a test that we could have done at the early stages to realize something is off in the data, but it was not part of our list of tests. So here you see the prediction for galaxy clustering conditioned on cosmic shear and galaxy-galaxy lensing. In that cross-correlation, systematics that affect only one of the samples will basically average out. So this should be robust to most imaging systematics and such. And you can clearly see here that for the red magic lens sample, there's something really off, and our PPD conditioned on galaxy-galaxy lensing and cosmic shear does not agree with the data. This works much better for the other lens sample that we had been developing, Maglim, but that was not ready to unblind on the same time scale as red magic. So then we basically waited for the Maglim team to finish their analysis and highlight those results in the paper, given that this diagnostic shows us that this sample should be more reliable, except for the highest two redshift bins, where you also saw in my earlier plots that the imaging weights had an enormous effect on the galaxy clustering. So likely foreground systematics are the limiting thing in this 3x2 point analysis at the moment.
Sorry,
Mm-hmm.
what is an imaging systematic for example? Because I see red magic is very different in the fifth redshift bin, below, above 10 minutes, right?
I mean, we only start at 10 arc minutes. We don't go below because we know that their nonlinear biasing becomes
Above, right? Above
Yeah.
10 arc minutes. What is an imaging systematic? What's the difference between the blue and the red?
So we have not fully tracked it down, but it seems to really affect our galaxy, our redshift fitting, or our redshift estimation. For red magic in particular, we require a really good chi-squared of fitting the red sequence. And if that red sequence is affected by reddening or such, then of course the goodness of fit is so bad that we throw out a lot of galaxies and have an incomplete sample. So that is, I think, something that is really important to realize, that at most unblindings you will learn something surprising, because data is always different. In the year 1, we had a poor goodness of fit and realized that that was related to shot noise modeling in the covariance. So then during year 3, everyone paid a lot of attention to the covariance, and we were hit by something completely different. Now in year 6, developing more of these consistency tests was the main thing on everyone's mind. But of course, data was again surprising. I think going forward, it's important to realize that even though you're analyzing this basically continuation of the same survey, as you go to higher and higher precision, you will likely discover different issues with the data that will need more attention. And we need to avoid just searching for our keys under the street light in terms of trying to only prevent the mistakes we made in the previous iteration. Those will probably get enough attention already. So with that, now with Maglim excluding the bins that are most affected by imaging systematics, we get to the fiducial constraints, shown here in blue and orange from cosmic shear and galaxy clustering, galaxy-galaxy lensing, which are now nicely consistent, which then combine into these black fiducial 3x2 point contours. And of course, we get some particular numbers out for S8 omega m and so on. And throughout the paper, we always quote both the marginalized parameters, 1D marginalized posteriors, and the map point, to give you some indication how much we think projection effects matter. And we think that at least for S8, in lambda CDM, they're reasonably controlled. In W CDM, that's a different story. Because even in 3x2 point, at the moment, we don't have enough constraining power to really constrain dark energy equation of states. So at the moment, the dark energy survey measures S8, but less so dark energy. Now, one robustness aspect of this analysis, answering a question from one of the previous lectures about the importance of baryon feedback. I'm highlighting here 2 re-analyses of both the year 1 as a 3 cos 2 point, and the DSK3 shear, where both of these analyses now remove the scale cuts in cosmic shear. So they increase the weak lensing signal to noise by about a factor 2, and then analyze down to small scales using different baryon models. The important thing to compare here is what I'm highlighting in the blue boxes. That is the fiducial DES analysis here, shown as the orange line, compared to an analysis including all scales with baryon modeling. So that's orange versus blue here, and solid, sorry, that box is wrong. I realize now. So here we have to look at dashed black versus red. That is DS scale cuts gravity only versus all scales with baryons. So I would say that these two are really pretty well consistent, which means that the contribution of baryonic feedback to the S8 tension appears to be rather minimal. Of course, if we go down to 2.5 arc minutes and analyze with a gravity-only model, green here, red here, then of course S8 gets biased low, because we do have this of order 20% suppression of meta-clustering that's not accounted for in the model. So that suppression then directly translates to S8 being biased low. Of course, when you analyze at DES scale cuts, marginalizing over baryons, where we know that baryons are poorly constrained, then you have to be careful how to interpret contours like this one. They have a 6-parameter baryon model, so projection effects at that point might be quite substantial. And I didn't want to call them out on this plot, with that plot here in my talk, but this paper includes a lot of other model changes. You can see here that their S8, also from the scale cuts, is pretty much centered on 0.8, which is quite a bit higher than what I showed in my previous slide. And that's largely due to differences in intrinsic alignment and redshift calibration modeling. So that shift there to S8 of 0.8 that's quoted in the abstract is due to a bunch of other factors, but not due to baryons. And I think I will conclude here. That was a lightning tour of weak lensing analyses. As you may tell from some of my comments on the site, I'm very happy to talk about any aspect more, but I also didn't want to bombard you with too many details. So I'm happy to answer questions. So, I mean, that is something that has been done in several papers already. In DS year 1, that was led by Simon Samarov. Recently, there was a paper on DS year 3 repeating that Elisa Legani and Jamie McCullough, I believe, were the lead authors, who primarily selected blue galaxies, or who basically tried to do a blue galaxy selection, at which point you have to redo the photo-Z calibration and shear systematics calibration, because you're dealing with a subsample. So this is substantial work, but at that point, they both found that blue galaxies are basically unaligned, and that can then substantially reduce the complexity and prior volume effects or projection effects in analysis. I am not sure yet what to make of the Euclid results for filaments, because of course that is a pretty particular galaxy selection. And in the end, we need something that holds for all blue or red galaxies. But this idea of splitting has been around for a while.
Has there been any incentive or where to go to explore for galaxy
I would not know why.
Can I ask you a
Yeah.
question? Because you were saying that this analysis make you confident that you're not so much dependent on baryonic physical small scales. So would you go as far as saying that if SA tension is real, then it is new physics? It has to be some high K, then it's new physics.
So,
What would it take?
I mean, there have been a bunch of really interesting weak-lensing results recently. I was most surprised or also happy about the recent kids paper, which I think is really a beautiful paper looking at various changes that they did between their previous analysis and current results. And for them, what really made a difference, and for them removed the SA tension, was changes to their photo Z inference, in particular also reducing sample variance. And I think, at least in these full samples, the impact of intrinsic alignments is not fully resolved yet. Part of the problem is that when you have to allow for different intrinsic alignment channels, so that is in the most minimal model just linear alignment plus a tidal talking term, then you get two free redshift amplitudes, and that causes enormous degeneracies and again projection effects. So yeah.
If this red contour was here,
Yeah. If you give me a moment, then I will actually now pull up one plot that I still find really interesting. Yes. So somehow they made a lot of choices, basically changing parts of the analysis that all tend to end up going to higher S8. Down here is the original DS analysis using tidal alignment plus tidal talking, two-parameter or basically four-parameter intrinsic alignment model plus shear ratio, that geometric information to constrain redshifts. Then when they simplify to just linear alignments, they find a shift up, and that's really weird because this analysis finds no preference for tidal talking. So those parameters are consistent with 0. And then you restrict to the subspace of that model where these parameters are set to 0, and you get a bias. So that basically tells us that the shift here is probably projection effects. Then they also, for some reason, decide to take out this geometric constraint on redshifts, which brings them up. Between here and here, the SNLA and their own halo fit pipeline. That just means that they haven't done their homework in terms of code comparison. We have two independent codes in the ES that make sure that we agree exactly. So this must just be some numerical bug.
that they have in the
Yeah. But then within their setup, they switch here between HaloFit and their own nonlinear meta power spectrum model. I would believe that that can cause of order of 0.3 sigma shift. Part of the problem was that at the time of this analysis, HM code 2020 was not out yet. On HM code, the original HM code did really poorly for galaxy clustering in the weakly nonlinear regime. And then the small change at the end, that is from baryons. So in the grand scheme of this plot, that's probably the least significant part.
Any other comment or question?
I guess I would still like to point out plots like this, I think, is why it's really important to do blind analyses and figure out how we want to make all these model decisions beforehand, so that we exactly don't go through these iterations based on how does it push me in the S8 plane. Okay. Of course, that can make you wildly unpopular. In the SU1, people had joked that the paper would be Abbott et al. Unless my insistence on blinding screwed up the results, then it would be Krause et al. So I'm happy to report it's Albert et al. Didn't get the first author paper, but it's good.